Welcome to the Causal Inference Reading Group. The plan for today is that I'm going to be explaining the chapter 3 of What If book of Miguel Hernan, which is on observational studies. Well, important to know is that I think last week a revised edition of the What If book has been released, and it's available online and it's free for everybody in case you wanna look it. I think there's a new chapter in this new version, but it's something that I have to double check. So that is the Christmas present for us. I'm gonna try to do it writing in an iPad because I don't know. I think it's more. I mean, I think it's useful to write rather than doing some slides or whatever. But I don't know, it's sort of an experiment. So we'll see how it goes, and then in the future we can change the method. Okay, before starting the chapter, a quick review of what we did what David explained us in the previous section. Of course, if anyone wants to ask whatever, like don't be shy, interrupt me. You can either raise hands with the Zoom option or maybe better directly talk and interrupt me. We want to have discussions. That's part of the goal of the session. So feel free to ask whatever. So David explained us last week how to estimate causal effects in randomized experiments, randomized experiments. And in particular, we study two types of conditions that guarantee that we can estimate causal effects from associational effects. The first condition was what we called exchangeability or full exchangeability, which means that the potential outcome under treatment A is independent of the treatment variable. This means that treated and untreated groups are exchangeable, which means that had the treated group not received treatment, they would have had the same risk or the same outcome than the non-treated group experimented. Okay. There was another condition under which we can estimate causal effects, which is what we call conditional exchangeability, which means exchangeability, but condition on certain variables. That means that within each strata of a particular variable L, we have exchangeability. Groups, treated and non-treated groups, are exchangeable within a strata of a variable. Okay, and then we saw how to estimate causal effects under both exchangeability and conditional exchangeability. And in particular, we studied two methods. One was standardization, and the other one was inverse probability weighting. So if our experimental design is such that conditional exchangeability or exchangeability holds, we can estimate causal effects from observational data, from the data using standardization or inverse probability weighting. And that was more or less a very quick summary of the previous chapter. The thing is that there is sometimes in which we cannot design studies such that one of these conditions holds. One can imagine, for instance, wanting to infer whether there is a causal effect or not of smoking in having lung cancer. If we wanted to do a study in which one of these conditions holds, we need to assign at random the treatment. That means making a person chosen at random to smoke during a certain amount of time and making a person chosen at random not to smoke during a certain time. And of course, that has a lot of not only logistical problems, but also ethical concerns. So ideally, what we could like to do is to be able to infer causality from data that is observational studies. To understand what is an observational study, we can recover the example of the looking up experiment. In the previous session, we had this experiment that was randomized. We throw a coin. If it's heads, a person will look up, and if it's not head, if it's tails, a person will not look up. And then we observe whether a second person that is in the scene is looking up or not looking up, depending on what the first person is doing. That's a randomized experiment, but if instead of that, we just measure, we just record a person that is looking up and record a second person that is coming, whether it is looking up or not, and we do the same with people that are not looking up, that's observational data. And of course, critics could argue that the two pedestrians are both looking up, not because the first one is looking up, but because they both heard a thunder, or there were some raindrops falling. That's more or less, this second design is an observational study. The first one is a randomized one. So once we realize that in not every experiment, we cannot design every experiment such that one of these two conditions hold, we need to know how can we infer knowledge, causal knowledge, from observational studies. Because much of the knowledge that we have comes from just observing the world without intervening in the world. So it's important to know how can we infer causal effects from this type of data. And the goal of the chapter is precisely that. The goal of the chapter is to determine conditions under which observational studies lead to valid causal inferences. And these conditions are called identifiability conditions. Identifiability conditions. This is the name because under these conditions that we're going to describe, we can identify causal effects using observational data. And the first thing to realize is that in the previous chapter, randomization implied exchangeability, and this was what allows us to determine average causal effects, for instance. Thanks to randomization, we had exchangeability in the treated and non-treated group. We could affirm with security that whether the treated people not have received the treatment, they would have experimented the same outcome distribution than the non-treated group. That guarantees exchangeability, that makes both populations exchangeable and allows us to determine the average causal effect. But in observational study, this is not generally the case. Exchangeability in general doesn't hold. Exchangeability does not hold in observational studies in general. And a way to understand this, a very simple example, is the example of heart transplant versus mortality. In general, when someone is receiving heart transplant, is generally having a worse condition than the ones that are not receiving them, because we prioritize people with worse conditions to receive the heart transplant. Imagine that those who are actually receiving the heart transplant are indeed more likely to have a severe heart condition. Then, had they not received the heart transplant, they would have been expected to have a greater risk of mortality than the ones that did not receive the heart transplant. That means that exchangeability is violated, is clearly violated. And we can think of many, like in medicine, many common examples in which exchangeability is violated because doctors do not assign treatments at random, but they do it depending on the value of certain conditions, which are generally related to the outcome. But in any case, sometimes we just have observational data, and we need to somehow determine causal effects. The solution for this, so in observational studies, the solution is to analyze data. Oh, I think, are you seeing my screen or not anymore? Yeah, can you see my screen?
Yes.
Okay, yeah. Sorry. I think my connection went weird. So in observational studies, the solution is to analyze the data as if treatment had been randomly assigned, conditioned on some covariates L. And the key thing is this condition on some covariates L. In the previous chapter, Hernan decided to introduce the concept of conditional exchangeability as experimental design. And I think they do it in purpose to prepare the stage to explain how to do causal inference in observational studies. So the key point here is that if we can find a set of variables such that within each strata of this set of variables, we can assume that conditional exchangeability holds, within those strata, we can treat observational studies as conditional randomized studies, and then we can infer causal inference. That's the trick. That's the reason why if you have worked sometimes with medical doctors, they try to adjust for or condition in many covariates as much as possible, hoping that within each level of these covariates, groups treated and untreated groups are exchangeable. Okay, so observational studies can be seen as conditional randomized studies under certain conditions, and the conditions are the following. The first condition is that in order to use an observational study as it was a conditional randomized one, the conditions are, first, that the values of treatment correspond to well-defined interventions. This is what we call before consistency. And we will go on these three in deeper detail in the rest of the session. The second one is that the conditional probability of treatment depends only on measured covariates. And this is exchangeability. And finally, the probability of receiving every value of treatment conditional in the covariate cell is strictly greater than 0, or what is the same, strictly lower than 1. And this is positivity. Okay. We're going to go through each of these properties, and that's the rest of the chapter. First, like these three hold by definition or by construction in randomized experiments. For instance, in the first one, if we have a clear intervention in the first two chapters, we were talking about clear interventions in which the values of the treatment correspond, like are very well defined interventions, like the heart transplant, receiving or not heart transplant. And we talked there about the multiple versions of treatment, defining precisely which treatment are we talking about. The second one holds by construction, because if a treatment is assigned at random, then the probability of the probability of receiving treatment depends only on the measured covariates in conditional randomized experiments, and does not depend in nothing in full randomized experiments. And the third one, the probability of receiving every value of treatment conditionally in L is greater than 0. That holds also by constructions, because for instance, in full randomized experiments, we give treatment with certain probability and don't give treatment with another probability. And both of them are greater than 0. Otherwise, we would not have two groups to compare. And now we will discuss these conditions in the context of observational studies. Okay, and here, well, just in number 2, they didn't say this in the book, but I think it's important. Like, they say conditional probability of treatment depends only on measured covariates, but also we could have that treatment can depend on a certain covariate X, such that X is independent of the counterfactual outcomes given L. This is something that can happen, and in the next section, we will understand why it's the case. So yeah, now for the rest of the chapter, we will discuss each of these three conditions. And we will start with the second one, exchangeability, which is, we'll go from the less philosophical to the more philosophical one. And the first one is exchangeability. We understood already that in randomized experiments, treated people, had they remained untreated, will have experienced the same average outcome as the untreated did, and vice versa. And this is because randomization ensures that all the independent predictors of the outcome are equally distributed between treated and not treated people. Let me write this because it's important. Like, randomization ensures that the independent predictors of outcome are equally distributed between treated and non-treated. That is, all the covariates that are associated with the outcome within levels of treatment are equally distributed between treated and non-treated people. For instance, if we design our heart transplant experiment as a randomized study, we will have more or less the same distribution of people with critical conditions between treated people and with critical conditions between non-treated people, because people were assigned at random to each of the groups, fully at random. In conditional randomized experiments, there is an imbalance in the distribution of predictors L between treated and non-treated is expected by construction. If we perform conditionally randomized experiments in which with certain probability we give treatment to people with a critical condition, and with a different probability we give treatment to people without that condition, then we will expect an imbalance in the distribution of predictor cells L between treated and non-treated people by construction. But the key thing here is that the rest of effects, the rest of predictors of the outcome are going to be equally distributed in both groups, because we are randomizing within each level of L. So we cannot find difference with in other covariates. If we go back to observational studies, when the treatment is not randomly assigned, there are reasons to, in general, for instance, there are reasons to receive treatment, and in general, those reasons are associated with the outcome predictors, right? For instance, if our reason to give or not a heart transplant is whether a person has a critical condition or non-critical condition, and clearly this critical condition affects the outcome, we will expect a difference in the distribution of these covariates between treated and non-treated groups. So the crucial question here for observational studies the crucial question is there a set of covariates that we will call L in general, such that those are the only outcome predictors that are unequally distributed between treated and non-treated. And this is the key. If this is true, then our design resembles that of a conditionally randomized experiment, and we can do causal inference. If this is not the case, then we cannot. And the key thing here is that those have to be outcome predictors. Of course, if we have a different distribution on a variable that is not an outcome predictor, we don't care. And this is what before we said. Treatment can depend on a covariate, but such that this covariate is not is independent of the potential outcome conditional in L. For instance, if we are doing this heart transplant experiment and we are using observational data, we collect a family of variables, L, that are related to the outcome, that are predictors of the outcome. We condition on those, and if we have an extra variable, X, such that is associated with the treated, the distribution of this outcome variable is different between treated and non-treated people, but based on our knowledge, we are completely sure that this variable does not affect the outcome. For instance, imagine eyes color. Eyes color, well, I'm not an expert medical doctor, but I guess that eyes color is not related with mortality, let's say. If we are very sure that that eyes color is not related to mortality, we don't care if eyes color is unequally distributed between treated and non-treated people, because it's not a predictor of the outcome. These variables that are predictors of the outcome and that are also unequally distributed between treated and non-treated are the so-called confounding factors. So the variables L are the confounding factors. And this is the reason why when doing a medical study, we always try to adjust for the possible confounding factors. Now, the relevant question here is that, sorry?
Can I make a question?
Yeah, sure.
Yeah, so so you said before that continuing your talk on medical studies, you said before that medical studies tend to record lots of variables, right?
Yeah.
That's in the hope that with those so many variables, they cover all the L.
That's,
and hopefully,
yeah.
Is that okay?
That's the hope. But in any case, and it's something that we will discuss in chapter 6, if I am correct, we need a way to identify somehow which are these covariates. In order to identify which are the confounding factors that we have to adjust for, we need a causal diagram of the problem at hand. We need causal assumptions, or also referred to as expert knowledge, if you want, of the problem at hand. And then if we have a set of causal assumptions of the problem, which are represented as a causal diagram, there is a criterion to determine which are these L. Oops, sorry. There is a criterion to detect which are these L factors, these confounding factors. And this is the so-called backdoor criterion, which was proposed by Jude Appel. And here is a connection between the two communities that we discussed the first day. The crucial question is, however, is this one. Is there a set of covariates L such that we can guarantee that those are the only outcome predictors that are unequally distributed between treated and non-treated? And there is no answer to this question, and this is important. There is not an answer. The only way to guarantee that this is the case is to use a randomized design. Otherwise, there is not a guarantee that this will hold. For instance, conditional exchangeability in observational studies will not hold if there is a variable U that is an independent predictor of the outcome, subject to the probability of receiving treatment A depends on U within each strata of L. So there could be always an unmeasured covariate that makes this thing fail. Even if we are very sure, that conditional exchangeability, if we are sure that conditional exchangeability holds, right? We can never check that this is the case. Like, for instance, if you are studying observational data about smoking and lung cancer, you can collect a lot of variables L such that you're very sure that this holds, but it's something that you cannot check. We could always say there is a gene that makes you crave nicotine, and at the same time, this gene is associated with lung cancer. We could say that there is such a variable, and there is no way for us to prove that is the case. So in general, this is an assumption of causal inference that is not falsifiable.
You mean, Roy?
Yeah.
So you say that there is a gene that we don't know yet. We haven't discovered it yet. That might. Okay, but you could say that given current knowledge, given current knowledge, that's the best you can do. And right?
Exactly, and that's what they do in causal inference, because in general, you cannot falsify this assumption. You can always invent something that says, if this is the case, then your conclusion is not correct, and you cannot prove that thing to be wrong. But this is the best you can do, and this is what they do in the community. But it's important at least to notice that causal inference from observational data on an assumption, which is this one, condition exchangeability, that cannot be empirically tested, and that's important. Okay, I forgot to mention before, but this is also interesting and is a sort of a break in the discussion that we are having. We mentioned that when we have observational data, we try to identify. I will put here like break, just a curiosity. When we have observational data, what we will try to do is to check for identifiability conditions. That is, we are gonna see if it is reasonable to assume certain things, and the first one is precisely the exchangeability or the condition exchangeability, in order to be able to infer causal effects from observational data. There is another way of doing causal inference. This is the first one, and is the one that is used essentially or most often in epidemiology. There is another way of doing causal inference, which are called the natural experiments. And are used a lot in econ, for instance. And I'm gonna just say a few words. They don't talk about the natural experiments in this book because they focus more in the first case. How can we define the identifiability conditions that allow us to make causal inference with observational data? But in econ, natural experiments are pretty important. And now that we know what is exchangeability and condition exchangeability, I think it's more or less easy to understand. Natural experiments are experiments that happen in nature that somehow are experiments that happen in nature that allow us to collect data that somehow we think that is reasonable to say that they resemble a random assignment. And the best thing to understand this is an example, which is by David Carr. I think it's David, right? Yeah, I think it's David Carr, which was a Nobel laureate in 2021. David Carr. And the experiment, he wanted to prove whether increasing the minimum wage was a cause for an increasing unemployment rate. And what he did, the way he solved this problem, which was pretty smart, he took two nearby states. One was New Jersey and the other one was Pennsylvania. And he realized that in one of those, I don't remember which one, I think it was New Jersey, there has been an increase in the minimum wage. But in the nearby state in Pennsylvania, there was not such an increase, right? And he studied the evolution of unemployment rate in both states. Why is reasonable to think that these two states could be exchangeable? The reason is that they are very close to each other. They are bordering states. So it's reasonable to assume that the job market will evolve in a similar manner in these two states. And then if the only difference in this evolution is that in one of the states, minimum wage was raised and in other was not, a change in the evolution of the unemployment rate can be due to the minimum wage increase. Okay, so somehow these two states, as a matter of being very close to each other, very similar in the rest of conditions, that thing makes those states exchangeable. This is an example of a natural experiment. So in econ, many people are dedicate their research to find these natural experiments that allow them to infer causal effects from observational data. And in the Wikipedia page, there is, I think, 5 or 6 examples of natural experiments. There is not this one, but which I think is very clear. But there are a few examples. And in particular, David Carr got his prize for the statistical method that he used to infer causal effect here, that is called the difference in the differences. Well, that's the end of the break. So we continue with the three assumptions that we need to make in order to infer causal inference from observational data. So the first one was exchangeability, and we hope to find a set of variables such that condition exchangeability holds, and we adjust for those variables. The next one is positivity. Positivity was something that was required, if you remember, in inverse probability weighting and in standardization. Otherwise, does not have sense. Like if mathematical sense, if positivity doesn't hold in, for instance, when doing inverse probability weighting, the inverse probability weight would be infinite for some cases because we will have a 0 in the denominator. And it's something that holds by construction in randomized and conditional randomized experiments. But clearly, we must guarantee that there is a probability of greater than 0 of being assigned to each treatment level. If there is a binary treatment, and we have one group, one treatment that has probability 0, then obviously we won't have people from that group, and the comparison is a nonsense. So what positivity means in general is that the probability of receiving treatment level A condition on L, on the covariate cell, is greater than 0 for all A and for all level L, subject to probability of L equal to L is different than 0. Of course, if we have a level of covariates such that there is no people with that level of covariates, we could define a new covariate L that excludes this group here, and then we just need positivity within those new levels. Okay. Obviously, in fully randomized experiments, this is in conditional randomized experiments. In fully randomized experiments, this means that positivity means that the probability of A equal A is greater than 0 for all A. And as we said, this holds by construction in randomized experiments. The important thing here is that positivity is only required for variables L needed for exchangeability, just for these ones. If we have another variable, for instance, the blue eye, the ice color that we said that is clearly based on our knowledge, not related to the outcome, so we do not need that variable to ensure exchangeability, we don't need neither to require positivity for this variable. Like we can still infer causal effects, even if all the people in the treated group has blue eyes and there are nobody with brown eyes within the treated people, because that is not related to the outcome based on our knowledge. So we don't need to require positivity for that covariate.
Excuse me. In case L were continuous variable, we will consider like a discretization of in bins or something like that, or
yeah, I'm gonna say something. I mean, what you need is that for every possible variable of L, value of L, no matter if it is discrete or continuous, you need positivity. Like what you do in general when L is continuous, or in the general case, we estimate this quantity, probability of A equal A given L, using a model. This is what is called the propensity score. They call it in general propensity score, and it's something that you need to estimate you need to estimate in order to do inverse probability weighting. This is the inverse of the weight. And if you need to do a standardization, you also need to estimate this. Usually, this is estimated via a parametric model, for instance, a logistic regression or another sort of model. Once you have a model here, you can check if this is a logistic regression, for instance, you can check that for every value of L, every possible combination of L, you have positivity. That means that this probability is not 0 and is not 1. What is usually done here is like you can, for your population, you can represent the propensity score for each level of the treatment. So imagine you have a population of 1,000 or 1 million people, and for each of these people, you can compute this propensity score, and you can represent it like a histogram. If this is 0 and this is 1, what you want to get here in order to guarantee that positivity holds is an histogram that is somehow in the middle, but is not reaching 0 and not reaching 1. If you had, instead of this, if you have something like this, that means that there is a set of values L such that you can perfectly predict for those values L that the treatment was, the probability of receiving treatment 1 was A, exactly A, right? Then positivity doesn't hold because there is a combination of L values such that the probability of treatment A is 1. And there are more ways to empirically verify if positivity holds, and they explain this in chapter something 11 or something like that. I don't remember. But this is one of the possibilities. And of course, the very simple thing of just if the sample size is big enough, we expect to see people at all levels of treatment for every value of L. For every combination of L, we would expect to see, if the sample size is big, the treatment in every level of people in every level of treatment. Okay, if positivity holds.
Okay, thank you very much.
Yeah. Okay, so how I am doing with time is okay. Well, and the last part of the chapter is consistency, and this is the most philosophical part of it. I'm just gonna, in the 15 minutes or 10 minutes that are left, I'm just gonna discuss a little bit. But I think it's worth reading it in the book. There are not a lot of maths here. It's just a discussion. We define consistency as the potential outcome under treatment A has to be equal to Y for every individual with that actually received treatment A. This is a very simple assumption, but this apparent simplicity is conceived. There are two ingredients in this assumption. First of all, there is in order to state that this is the case, we need a precise definition of the potential outcomes. And this implies that we need a detailed specification of the possible levels of the treatment. And the second is that we need some kind of link between YA and the observed outcome Y. Okay. And then the rest of the chapter, they just discuss these two ingredients. And I'm going to just say a few words in each of them. The first one is that we need a fully specified treatment. We need to fully specify each treatment level. And sometimes this is very hard in observational studies. In studies such as giving a treatment to a person or not, this is easy, like doing a heart transplant or not. We just need to specify what is the heart transplant, who is the doctor, what is the technique, and some of the things that we think that is relevant for the outcome. And with that, we can fully specify each level of treatment. But in observational studies, this is sometimes more complex. For instance, we could think of trying to estimate the effect of being obese at age 40, obesity at age 40, with mortality risk at age 50. And here there could be many versions of the treatment, because there are many ways in which someone can be obese at age 40 that clearly affect the outcome. For instance, someone could be obese at age 40 because he or she has some genes that make them be obese at that age. Or someone could be obese at that age because they don't do a sport and they eat a lot. Someone could be obese at 40, but have been obese for a very long time. And someone could just be obese at 40, like after a year of eating a lot. And how you are obese at this age will clearly have an effect on mortality risk. So we need to precisely define the ways, the treatment, the ways in which someone is obese at this age. Of course, absolute precision is not needed, because there are some aspects of treatments that are deemed irrelevant because varying them leads to the same counterfactual outcome. So the conclusion is that we need to specify, we need sufficiently well-defined interventions. But in general, what is a sufficiently well-defined intervention is something that we cannot determine, and is something that depends on the agreement of experts. Like, the experts have to be the ones that define precisely the interventions. And as the experts are the ones defining this, the articulation of a causal question is contingent on the domain of expertise, and it's an informal judgment. A scientifically meaningful causal question today might not be meaningful after years, because we learn something new that makes us make a different statement about the intervention.
Right.
Yeah.
Can I make a question?
Yeah.
So I want to ask whether this would be an example for this. For example, for the WHO guidelines for physical activity, they tell us, as I'm an old person now, they tell us to do like 30 minutes per day of exercise. So that would be like a sufficiently well-defined intervention. I mean, why 30 and why not 35? Well, some guys that in Switzerland have said that we should do 30 minutes all this.
Yeah,
that would be an example of.
Yeah, in that case, that's sufficiently well defined, and it's an intervention that is much easier to define than being obese at age 40, right? Because in that case, it's like a treatment. There is a version of treatment that ideally you would want to specify more, like say 30 minutes of a sport, of this particular kind of a sport, and in this particular way of doing it. But if you manage to do that, then that's sufficiently well specified. If you just say doing 30 minutes of any sport, then it's less specified, and what you will end up doing there, you will end up inferring causal effect of 30 minutes of any sport. But clearly, for instance, if you are trying to study mortality, for instance, risk of mortality, and this sport is, for instance, climbing Everest in 30 minutes, clearly that's related to mortality risk, right? And you will be including those into your statistics, so to say.
Okay.
So that's the reason we need precisely specified interventions. What they say here that for me is illuminating is that, for instance, if you do not define sufficiently well the interventions, for instance, in the obesity example, you just say, I collect some data and I divide my people between people that are obese at age 40 and not obese at age 40. And I study mortality risk at age 50. That corresponds to the intervention of making someone that is 40, automatically non-obese or automatically obese by changing that person genetically. That's the corresponding intervention that we are studying, because we are not considering anything else, right? And that's tricky, but is what happens here. If we define better our causal question and our intervention, we could say, okay, we want to study all the people that are obese at age 40, but that had been obese from age 20 to age 40, and we exclude from this study the people that had not been obese from age 20 to age 40, then you are changing your causal question, you are making it different, but specifying more who is in the treated group and who is not in the treated group. And this will correspond to a more realistic intervention, right? Well, just, okay. So in the last 5 minutes, they end up discussing the concept. Well, they say a few more words about the link between YA and Y. And the key thing here is that that you need a clear connection between treated people and non-treated people using the data. If you restrict your treatment A, if you restrict your treatment A and you make a very precise definition, it is possible that you would not have enough data to determine whether someone is in the treated and non-treated group. So there is this trade-off. For instance, if you, in the obesity example, if you say, okay, my definition of obese at age 40 could be someone that has been obese since age 20, right? Saying that the IMC, I don't know how it's in English, the body mass index, the BMI, is greater than a certain value since age 20. You have a more precise definition of the treatment, but you also need data to verify that someone is in that group or not. So you would need, for instance, data about the body mass index of this person in the last 20 years. And it's important to have a connection between the data and the definition of the interventions that you are considering. And then they end up the chapter discussing what they call the target trial. They say that it's very helpful to use this concept of target trial when designing a causal experiment. The target trial is nothing else than a hypothetical experiment, randomized experiment. And we use observational data to emulate this experiment. So for every causal question, if we want to define a target trial, we need to, if we want to determine causal effects from observational data, we will need to do two things. The first one is define a target trial. And the second one, say how observational data is used to emulate it. Of course, if we want to define a target trial, we will need to define a few things, as which is in this hypothetical randomized experiment, the eligibility criteria, who is going to receive treatment or not, which are going to be the particular interventions, which are the outcomes, what is the follow-up, what is the causal contrast that is being done, and what is the statistical analysis. And most likely, if we start thinking about the target trial, our causal question is going to be different. Like if in the obesity example, if we say, okay, we are going to think in a target trial, like in a hypothetical randomized experiment, we would need to think to say what is the intervention that we do to the people. The intervention would be, for instance, to give diet and exercise to people such that their body mass index is below a certain value from age 20 to age 30. That's a very well-defined treatment. And then we need to identify individuals in the observational data that follow that treatment or that does not follow that treatment. And for me, the most interesting thing that they say here, well, they say that not everybody agrees with the view of causal inference from observational data as an emulation of a target trial. They say that it could be the case that we don't have a target trial, but if there is a very strong association between obesity and mortality, this may imply that there is some intervention on body weight that reduces mortality, but we don't know this intervention is not clearly well designed. And that is true. You can determine that that is the case. But from a practical perspective, is from a purely decision-making perspective, if you have a target trial with a thought experiment of how will you intervene the people, you are not only identifying a causal effect here, but also you are identifying interventions that are that could help with the effect that you are measuring. For instance, if you have a very well-defined definition, a very precise definition of obesity here in this mental experiment, and you determine that this reduction of obesity in this way helps with mortality, reduces mortality, you not only have a causal conclusion, but also a way to articulate that causal conclusion in reality. You could take this intervention and propose it for a population, which is an example of what David says before about the 35 minutes of exercise. While if you don't have a very precise intervention defined, you know that there is a causal effect, but you don't know how to articulate that. Like you could know that there's a causal effect of being obese at age 40 with mortality risk, but you don't know you don't know if it is because being obese comes from a genetic intervention or if it comes from a good diet or if it comes from doing exercise. So in practice, you cannot do nothing. And well, they finish the chapter saying that there are many cases in which these assumptions that we define for observational studies are not realistic at all. And in those cases, you cannot do causal inference, but you can do prediction, association, generate hypotheses, which is what people do in statistics and in machine learning classically. And while you cannot determine causal effect from that sort of experiments, you can generate hypotheses that maybe in the future are going to be causally studied. And this is more or less the chapter. Now, if there is any questions or comments, we are happy to listen and to discuss. It's this was more philosophical, so to say, than the previous one. It's not as practical, but I think reading it is useful. It's quite illuminating.
So, Roy, I would like to make a question. In this last part that you said that you can do a causal inference, but you can do prediction. So you would, let's say, do the same math, but you would just could mention association, but not causation. That's the message of the these two last paragraphs.
Yes and no. I would say that it's not always the same math, because there are methods which are particularly tailored for causal inference. But of course, those methods will help you determine causal effects as long as some assumptions hold. So there is new math that is motivated by causal inference, but of course, you always need assumptions to determine whether there is a causal effect or not.
But the association measures and the what was the other one? The effect measures.
Mm-hmm.
I mean, they look alike, quite similar. Rather, I mean.
Yeah. They are exactly the same. They are
right.
Mathematically they are the same, but how you compute them, I mean, like they are the same, and if there are some assumptions, one is equivalent to the other, and if there is not those assumptions, then no. But there are more complex cases in which there is new math that has been motivated by causal inference.
Okay.
Like for instance, how do you estimate the probability of a counterfactual given L from data? This is something that given L and A, sorry. Like there are methods to do it which are brandly new in the sense that they have been proposed by or motivated by causal inference. But obviously they are just gonna be equal to probability of Y given A and L if there are some assumptions here. Otherwise, no.
Okay.
Yeah. I think Alice raised hand a while ago.
Yeah, well, thank you. Thanks a lot first for the description of the chapter. I have a question, but I don't know if it's too naive. So when we talk about exchangeability and all this, we see them as like binary properties. So two variables, either they're exchangeable or they're not. Is there like, is it something that has been studied, whether you can do this transform it into like a continuous thing? So to define a measure of exchangeability and then to make causal statements based on this measure, like, I don't know, like there's some probability of these variables to be like one cause influence of the other or stuff like this.
Yeah, it's a good question. Well, I don't have a very clear answer. I think your question is equivalent to saying have people studied causal inference for continuous treatments, right?
Yeah, yes.
Which, because for us, exchangeability was between group without treatment and group with treatment. If instead you have a treatment that is continuous, how do you define exchangeability here? Because so to say, you have infinite groups, right? One
sure, yeah,
for
okay,
each of the possible variables. And this is, I mean, it's definitely studied because sometimes they study like the treatment definition implies, for instance, the dosage of the treatment that you receive.
Mm-hmm.
But what I guess that they do is discretize these variables. So like, for instance, if you are studying dosage of a treatment, you convert it in no dosage, 100 milligrams, dosage 200 milligrams, right? Mm-hmm. For instance. Studying the whole, I mean, I like for sure there are studies in which they do not discretize and they consider the treatment variable as a continuous variable and they do things, but I don't know how they work. But there are things, definitely.
Okay, so if there's no more questions and I can borrow a bit more of the time. So
yeah, sure.
When we define exchangeability, is that essentially this P of YA given A was independent of the choice of A, right?
Exchangeability is that the counterfactual is independent of A. This is full exchangeability, and condition on L is condition exchangeability.
Exactly. So this is essentially that the P of YA given capital A is independent of the value of capital A.
Yeah, exactly.
But then you can define, or you could think of defining something like P of, I mean, this is something that David mentioned last time. So P of YA given A equals 0 minus P of YA given A equals 1.
Yeah.
And this could kind of give you a measure of exchangeability. So if it's 0, then they are exchangeable, and if it's non-zero, then they are not exchangeable. But there's some sort of like magnitude of how not exchangeable they are.
Sure. And
is this a thing that people study, or is something that people try to make statements about, or like to quantify the causal influence in the basis of this sort of quantities?
Well, I'm not sure if they are doing this, but it seems unlikely because these two quantities are quantities that you can estimate from data just in the case in which this thing holds. So you can estimate this just in the case in which this
Yes.
is 0, right? Because
Yes.
otherwise you cannot estimate counterfactuals,
Yeah.
probability of counterfactuals from data.
Yes, you're right.
You need,
you're right.
yeah, but I don't know, there might be something, or at least in some thought experiment or whatever.
Okay.
But
Well, thank you very much.
essentially, yeah, I think if you want to estimate those quantities, you need the exchangeability to hold, and you want this magnitude to be 0.
Yeah, it makes sense.
Yeah, but it's an interesting question.
Thanks.
Okay, are there more questions?
Yeah, I have a question and maybe a comment about Alex's question. So if I can start with the last one. I'm not sure if I fully understood Alex's question, but I think sometimes there are, when people are concerned about whether exchangeability holds or not, they study how different deviations from exchangeability affect the results of the inferences. So that goes under sensitivity analysis. Rosenbaum and the book by Morgan and Winship go in detail over this issue. So basically, what you can think of, like, if you have a hidden variable that you haven't measured, how that variable affects the correlation between the treatment and the potential outcomes, and then, like, given it's a correlation, just go over the range or sweep over that variable and see how your estimates of the average treatment effect are related. I'm not sure if this is related to your question, Alex, but if it is, maybe that's a way of trying to deal with it. Is this something that makes sense, Roy, what I'm saying, or am I?
Yeah, like, as I don't know precisely the result you're referring to, but as I think of it, is like, imagine I have a set of variables that I measure and are the ones that I consider that are the confounding factors, right? So I have to adjust for them, and with them I compute an average causal effect. Then assume that I have another set of variables, U, that I do not measure, that I measure as well, because otherwise I cannot do nothing, that I think that are not confounding factors. But just in case, I'm gonna measure the causal effect, adjusting not only for L, but for the union of these sets, or all the possible combinations of variables from these sets and this one, right? And then I measure average causal effect. If in every case, the average causal effect, like the drug works, so to say, right, or whatever experiment, then I'm pretty sure that no matter which are my variables here, I have this average causal effect. So it's kind of a sensitivity analysis to the hypothesis that these are the only confounding factors. So,
but I think you can I think some authors actually take it further, because we regard the U variables like really as unobserved, and you just ask the question, let's assume there is some known or non-measured variable that's causing a correlation between the outcome and the treatment. What are plausible values of that correlation, and under those plausible variables of plausible values of that correlation that's induced by the hidden variable, how is our average causal effect? And it's sort of like a kind of preemptive way of saying, well, maybe I have not measured something, but that stuff I have not measured, do you really believe it could be producing such an extreme effect that will say revert the average causal effect or turn it to 0 or something like that?
I mean, it's a possibility. Related to that, there is, like, we haven't talked yet about how to estimate those variables, and I mentioned that this is what has to do with the backdoor criterion. There are other ways of doing, like, there are other sets of variables that you can adjust for, which are not necessarily confounding factors. That's called the front door criterion, and is discussed in Judea Pell's book. And in that case, under another set of assumptions, you can still have unmeasured confounders, and determine causal effects. But there is another set of assumptions which, of course, are not falsifiable again. And if those assumptions hold, you can still estimate causal effect, even if there is unmeasured confounders. But I don't know if they discuss it in this book, but they discuss it in Judea Pearl's book, and maybe something related to what you are talking about. Yeah, and of course, I mean the precise result you are saying, I don't know it, but yeah, it could be like there could be some other methods, which I'm very convinced is that no matter what is the method, there are always gonna be assumptions that you cannot verify empirically. That's the nature of the problem.
Can you repeat again what you said about Judea Pearl's approach? Because I couldn't write it in full.
Yeah, so the approach to determine which are the confounding factors based on the causal knowledge is the backdoor criterion.
Yeah, and then the next thing you said was.
And the next one is that there are some situations in which even if you cannot measure all the confounders, you can still estimate the causal effect, and it's called the front door.
Okay.
Is this one, and they have a very nice example in the book, causal inference in statistics or something like that. They have a very but of course you need a different set of assumptions to estimate causal inference there.
Okay, thank you. And do we have time for a silly question about the comment you made in the break?
Yeah, I have time at least.
So this study where you said the natural experiment, how would the logic of the natural experiment still hold if there is migration between the two different states? I mean, if there is migration of workers between the two different states, isn't there going to be something like you are actually changing the job market, so the natural experiment is no longer working as you? Am I getting it completely confused, or is?
No, I think it's a relevant question, definitely. I mean, I guess nobody has an answer on that, but you have to make a set of assumptions and such that you think it's reasonable to consider the two populations as changeable, and that's it. Of course, there could be some violations of that you cannot take into account, but it's the best you can do, so to say.
So if people started moving between states, like changing residence, that would sort of like kind of start violating the assumption of exchangeability, or not necessarily?
Well, in that case, I'm not sure. I mean, in the precise case of the two states, like the important thing is that they perceive or not the minimum wage raise.
Okay.
So I know. I mean, you study the work affiliation of a person, and well, if the work affiliation is different from where they live, I could say it doesn't matter as long as. I mean, if you are measuring minimum wage increase and unemployment rate, and for that, the work affiliation is the only thing you need, I guess. But yeah, of course, are things that they need to take to account for.
And this whole thing, is it somehow related to the instrumental variables approach, or is not really the same thing?
Instrumental variable analysis is another way of estimating causal effects without identifiability criteria. And I don't know. I mean, I don't know if it is related, but definitely, if there are two groups of manners of estimating causal effect, one is by trying to have identifiability conditions, and the other one is the rest. The instrumental variable analysis will be here, definitely.
Okay.
I don't know much about the instrumental variable analysis, but well, just what I know is that what they do, they try to do is like, for instance, you cannot do a randomized experiment in which you make some people smoke and some people don't smoke, but what you can do is a randomized treatment in which the treatment is you give some sessions to encourage people stopping to smoke, and at random you select some other people that don't have that treatment. And if that treatment is somehow related to the original treatment that you are interested on, based on some other conditions, then you can estimate causal effects. It's not a natural experiment, definitely, because in natural experiments you don't.
It's not a natural experiment then. So they are different sort of approaches, right?
Yeah, because in natural experiments you never intervene.
Okay, all right, thank you. I got it confused then. All right, thank you very much.
Okay, so well, just a quick announcement for the next year. This is the last session of the year, and the next year we already have volunteers for the next 3 chapters. Our Simon will do chapter 4, Chema will do chapter 5, and David will do chapter 6. And of course, if anybody want to volunteer, we would like to have a list that we can use for the next session. So you are welcome. And also, if you want to discuss something else, not necessarily related to the book, but related somehow to causal inference, just let me know, and I will put you in the list with the material that you want to discuss. And yeah, that's it for today. Thank you very much, and see you next year.